We're going to start off with this first slide that talks about quartiles. And quartiles are pretty easy to understand if you understand the concept of percentiles. So a good example for that would be the 90th percentile of a data set is the point that divides the bottom 90% of the data from the top 10% of the data. So for example, if you got in the 90th percentile on the SAT, that means that you scored better than 90% of the students who took the SAT, and 10% of the students who took the SAT scored better than you did. Quartiles are just the 0th, 25th, 50th, 75th, and 100th percentiles. So as you can see on this slide, it says Q0 is quartile 0, which is just the minimum of the data set. Q1 is the 25th percentile. So that means that Q1 is the point that divides the bottom 25% from the top 75%. In other words, Q1 divides the bottom quarter of the data from the top 3/4 of the data. And so that shows you where the term quartile comes from. Quartiles are just the points in the data set that divide it into quarters. So then we have Q2, which is the 50th percentile. In other words, Q2 divides the bottom 50% from the top 50%, which is the same thing as saying that Q2 divides the bottom half from the top half. And so you can actually see that Q2 is just the median. And Q3 is the 75th percentile, which divides the bottom 3/4 from the top quarter. And Q4 is the 100th percentile, or the maximum. This slide shows how we can find the median, which is just the middle number of a data set. So if we take a look at this first data set, we have 1, 3, 5, 7, and so on and so forth. You can see that the middle number there is the number 10. And so that's the median for that data set. If we look at the second data set here, we have 1, 5, 8, 9, and so on. Well, here we don't have a clear middle number because there are an even number of things in this data set. There are 8 numbers in this data set, and so there's no clear middle number. We actually have 2 middle numbers. We have the numbers 9 and 10. In a situation like that, we just average those 2 middle numbers. So we're going to take the average of 9 and 10, and we're going to get 9.5. So the median of that data set is 9.5. The first example worked really nicely because there are an odd number of things in that data set. We have 9 elements of that data set, and so there was an actual middle number. Now we're going to take a look at finding the first quartile, which is just the 25th percentile of a data set. The first quartile is the point that divides the bottom quarter of the data from the top 3/4 of the data. Now, really that's actually the same thing as saying that it divides the bottom half of the data set into 2 equal pieces. In other words, the first quartile is actually the median of the bottom half of the data set. So if you're ever trying to find the first quartile of a data set, just find the bottom half first, and then find the median of that bottom half. Let's take a look at this first example with the numbers 1 through 19. So we need to find the bottom half, and that requires us to find the median. So we already saw on the previous slide that the median of this first data set is 10. And so the bottom half is going to be 1 through 10. It's going to be 1, 3, 5, 7, 10. So the first quartile is actually the median of that bottom half, which is 5. That's the middle number in that bottom half. And so that means that the first quartile in this first example is the number 5. Okay, let's go ahead and look at the second data set, which consists of the numbers 1 through 15. Again, we just want to look at the lower half of the data set, and then we want to find the median of that lower half. So in order to find the lower half, we need to start off by finding the median of the big data set. And we saw on the previous slide that since we have 2 middle numbers, 9 and 10, the middle number here is going to be 9.5. And so that means the bottom half of the data set is going to consist of the numbers 1, 5, 8, and 9. We're not going to include the number 9.5 in this situation. So the lower half just consists of the numbers 1, 5, 8, and 9. And now we want to find the median of that lower half. And so you notice here that we have 2 middle numbers, 5 and 8. So we're just going to take the average of those two numbers. 5 plus 8 is 13. 13 divided by 2 is 6.5. And so the first quartile for the second data set is 6.5. Finding the third quartile of a data set is very similar to finding the first quartile, except that you're going to find the middle number in the top half of the data instead of the middle number in the bottom half. Let's take a look at this first example consisting of numbers between 1 and 19. We want to find the top half of the data. As we saw before, the median for this example is 10, and so the top half of the data consists of the numbers 10, 13, 15, 17, and 19. The middle number of this top half of the data is 15, and so the third quartile for this first example is 15. Okay, let's look at the second example that has numbers between 1 and 15 in it. We want to find the top half of the data. As we saw before, the median is 9.5, and so the top half of the data consists of 10, 11, 12, and 15. We want to find the middle point of this top half of the data. Since we have two middle numbers, 11 and 12, the midpoint of this top half is 11.5, and so the third quartile for this data set is 11.5. The interquartile range of a data set is a very simple concept. It's just the distance between the first quartile and the third quartile. So looking back at the two examples we just covered, for this first data set, the first quartile was 5 and the third quartile was 15. And so the interquartile range there is just 15 minus 5, which is 10. For the second example we were looking at, the first quartile was 6.5 and the third quartile was 11.5. So the interquartile range is just 11.5 minus 6.5, which is 5. Now we're going to start talking about ways of measuring the spread in a data set, and we're going to be looking at these two samples that consist of numbers between 5 and 15. You guys have already talked about the range of a data set, which is just the maximum minus the minimum. So for both of those samples, the range is just 15 minus 5, which is 10. And we just looked at the interquartile range, which is the distance between first quartile and third quartile. You can see for the first sample, the first quartile is 9 and the third quartile is 11, and so the interquartile range is 11 minus 9, which is 2. And for the second sample, we're going to get a first quartile of 6, a third quartile of 14, and so the interquartile range is going to be 14 minus 6, which is 8. The most important and most commonly used measure of spread for a data set is called the variance. The variance is based on the idea that we would like to be able to measure the average distance from each observation to the mean. Another way that we could put that is we want to measure the average amount that each observation deviates from the mean. Okay, let's take a look at the concept of variance in more detail. Basically, in order to find the variance, you have to start off by finding something that's called the sum of squared deviations. And to find the sum of squared deviations, you're just going to take the distance from each number to the mean, and you're going to square that, and you're going to add them up. So the distance from each number to the mean is called the deviation of that number from the mean. And so you're just finding all of those deviations, squaring them, and adding them up. Again, we're going to be looking at these two examples that consist of numbers between 5 and 15. So let's go ahead and look at that middle bullet there, where it talks about finding the sum of the squared deviations for let's say for sample 1. Now, sample 1 has a mean of 10. So to find the sum of squared deviations, we're just going to take each number, subtract it from 10, take that result, and square it. So we're going to look at 5 minus 10 squared. Then we're going to do 9 minus 10 squared, and 10 minus 10 squared, and so on and so forth. And you're just going to add all of those numbers together, and that gives you your sum of squared deviations. And that number is equal to 52. For the second example, the mean is also equal to 10. So we're just going to take each of these numbers, subtract 10 from it, square that result, and add all of those results together. And we end up getting 82. So the sum of the square deviations for the second sample is 82. Notice that in both of these examples, some of these subtractions are giving us negative numbers. It's important to keep in mind that when you square a negative number, it's going to turn into a positive number. For example, 5 minus 10 is negative 5. We're going to square that negative 5 and get a positive 25. Once you have the sum of squared deviations, finding the variance is easy. To find the variance, you're just going to take the sum of squared deviations and divide it by the sample size minus 1. For both of these examples, the sample size is 5, and so the sample size minus 1 is 4. And so let's say we want to find the variance for the first sample. We're just going to take the sum of squared deviations, which was 52, and we're going to divide that by 4, and we're going to get 13. And for the second example, the sum of square deviations was 82, and if we divide that by 4, we get 20.5. And so the variance of the first sample is 13, and the variance of the second sample is 20.5. This slide has 2 equations on it, and let's start off by discussing the first one. The first equation is actually a convenient formula you can use to calculate the sample variance, and it actually just mirrors what we discussed on the previous slide. Now, before we discuss the equation, I want to just talk about what each of the symbols are in the equation. So S squared represents the sample variance. That n represents the sample size, the number of things in our sample. The xi's are the individual numbers in the data set, and the x bar is the sample mean. That capital sigma, Greek letter sigma, the way that we read that is we say summation from I equals 1 to n. That represents the fact that you're adding a bunch of things together. So if we think about what that equation is telling us to do, it says xi minus x bar squared. Well, that means take each individual number in the data set and subtract the sample mean and then square that result. And then that sigma, that capital sigma, is telling us to add all of those results together. So that's actually just the sum of squared deviations that we were looking at on the previous slide. Then finally we have the 1 over n minus 1 in front. Well, that means divide that whole result by the sample size minus 1, again, which is what we did on the previous slide. Alright, now let's talk about the second equation on the slide. As before, we'll just say what each symbol means first. So the symbol on the left is a lowercase sigma. Lowercase sigma squared is the population variance. On the right, we have a capital N, which represents the population size. In other words, the number of people or subjects in our population. Again, we have a capital sigma, which is a summation symbol, which means to add things together. And then we have an xi, which represents each individual number in the population. And we have mu, which represents the population mean. So this equation basically just says that the population variance should be calculated in the same way as the sample variance, except that we divide by n instead of n minus 1. And we'll discuss the reason for that on the next slide. But as Dr. Shi discussed in the first part of the lecture, you would only be able to use this equation if you actually collected data for every single person in your population, and so you're almost never going to actually be able to calculate the population variance. But it's still an important concept that comes into play in some of our equations later in the course. Alright, the purpose of this slide is to discuss a little bit why the denominator of this variance equation has an n minus 1 in it instead of an n. Before we can discuss that, though, we need to say a little bit about what is the purpose of the sample variance. So there's 2 types of variance. There's a population variance and a sample variance. And the thing that we would really like to know is what the population variance is. But we can't very easily calculate that because, like we said before, to find the population variance, you have to collect data for every single individual in the population, and that can be extremely time-consuming and expensive. So instead, we're going to take a sample from the population and then just calculate the sample variance and use that as an estimate for the population variance. And we would like that sample variance to be a good estimator for the population variance. We would like the sample variance to be about the same size as the population variance. We don't want the sample variance to be a lot smaller than the population variance or a lot larger than the population variance. On average, we want the sample variance to be equal to the population variance. And this is referred to as unbiasedness. So it turns out that the way to make that happen is to put that n minus 1 in the denominator of the equation. And you can see a proof of that in a more advanced mathematical statistics course. We can actually say a little bit more about why the denominator of the variance equation has an n minus 1 instead of an n. And that's because n minus 1 is the number of degrees of freedom in this equation. Okay, so what does degrees of freedom mean? The best way to describe that is to look at this equation x plus y equals z. In order to determine the degrees of freedom in this equation, we have to ask ourselves the following question. How many variables in that equation can be assigned freely? In other words, how many times can you just choose a random number and plug it into this equation and still make the equation work? Now you might think that you can just assign all three variables freely, but you can't. Because let's say we assign a number to x. Let's say we decide x is equal to 5. This isn't coming out of anywhere. This is just we're freely making up a number to plug in for x. Nothing's really wrong yet. I mean, x is 5. Okay, that's fine. Let's go on to y now. Let's say we want to just make up a value for y. Let's say we plug in 7 for y. Okay, so x is 5 and y is 7. Okay, now let's go on to z and let's make up a number for z. Oh, wait a minute. We can't make up a number for z. Because if x is 5 and y is 7, z has to be 12. So as soon as we assign a value to x and we assign a value to y, the value for z is automatically determined. So there are only 2 degrees of freedom here. Another way to look at it is it doesn't matter which variables you assign. Let's say you plug in 4 for x and you plug in 10 for z. Well, then y would have to be 6 in order to make the equation true. So you can only freely assign values to 2 of the variables in this equation. In other words, the equation x plus y equals z has 2 degrees of freedom. So the equation x plus y equals z had 3 variables, but you'll notice that the degrees of freedom was equal to 2. So usually the degrees of freedom in an equation is going to be equal to the number of variables in that equation minus 1. Now if we return to the equation at the top of the page, which is the equation for the sample variance, it makes more sense now that the degrees of freedom is equal to n minus 1, and that's because it's a little more complicated than this, but it's essentially because there are n variables in the equation. The n variables in the equation are x1, x2, and so on up to xn. And those x's are related to each other, and I don't want to get too much into the details, but it has to do with the fact that the sample mean is related to the x sub i's. So to make a long story short, there are n variables in that equation, and they're related to each other, and therefore the degrees of freedom is n minus 1. Alright, this slide has the formula for the population variance again, and we've pretty much said all there is to say about this slide, so let's just move along. This slide just provides another example of calculating the sample variance. Remember that the first step in finding your sample variance is to find your sample mean. So if you add all these numbers together, you'll get 24, and then if you divide that by 4, you'll get 6. So the sample mean is 6. And let's just go over how to calculate the sample variance again. You're going to take each element of your sample, subtract the mean, square that result, add those together. So you're going to take each number here, subtract 6, square that, add those all together. That gives you 10. And then you're going to divide 10 by 4 minus 1, since your sample size is 4. So you're going to have 10 divided by 3, which is 3.3. And again, that's just what this equation in the middle of the slide is saying to do. Also recall that once you found your sample variance, you can just take the square root of that to get your sample standard deviation. So in this example, we just saw that the sample variance was 3.3. So if we take the square root of that, we get 1.8. It's that simple. So in this course, we're going to encounter a few different types of variance and standard deviation, but all you have to remember about the standard deviation is it's the square root of the variance. So as soon as you find your variance, just take the square root of that, you get your standard deviation. Nice and simple. This slide has a histogram for a sample of 200 adults' heights. A histogram is just a bar graph that we use to display statistical data. On the x-axis, we put the variable of interest to us, which is height in this case, and we're measuring height in inches here. On the y-axis, we put frequency, which is the number of people in each category. So, for example, if we look at the left-hand side of the graph, and we look at the number 61, the height of the bar above 61 is equal to 1, and so that means there's one person in this sample with a height of 61 inches. The bar above 62 has a height of 4, and so there are 4 people in the sample with a height of 62 inches, and so on and so forth. You can also see that most of the people in this sample have a height somewhere around 68 inches, And in fact, if you look at the bottom of the table, it says that the mean is 68.2 inches and the standard deviation is 3.1 inches. You'll also notice 5 vertical reference lines in this graph. The center line is located at the mean, at the point 68.2. The 2 lines immediately to the left and the right of that line are a distance of 1 standard deviation away from the center line. So the center line is located at about 68, which is the mean, and the standard deviation is about 3. So if we take 68 minus 3, we get 65, and you notice that's where that line to the left is located. And if we take 68 plus 3, we get 71, which is approximately where the line to the right is located. Then we also have 2 lines at the far left and the far right, and those are each a distance of 2 standard deviations from the center. And so, again, going through that calculation, the mean's about 68, the standard deviation's about 3, so 2 standard deviations is 6. 68 minus 6 is 62, which is where the far left line is located, and 68 plus 6 is 74, which is about where the far right line is located. Again, these numbers aren't matching up exactly because the mean is actually 68.2 and the standard deviation is actually 3.1. Finally, you'll notice that there's a red curve in this graph. That red curve is a normal probability distribution. Now, a normal distribution is basically just a bell curve, and it represents what the histogram would look like if the sample were perfectly normally distributed. And you can see that the sample is reasonably well approximated by a normal distribution, but it isn't exactly normally distributed. Now we can talk about Chebyshev's rule. Chebyshev's rule says that if you look at all of the data that's within 2 standard deviations of the mean, that will be at least 75% of the data points. It could be much more than 75% of the data, but it has to be at least 75% of the data. In other words, if you consider the graph that we were talking about on the previous slide, and you look at all of the points that are between that far left reference line and that far right reference line, at least 75% of the data will be in that range. Now, if you actually count it up, there are actually about 193 observations in that range, and there are 200 total people in our sample. So actually about 97% of the data is in that range. So, it could be a lot more than 75%. Chebyshev's rule is a rule that works for any probability distribution. So for some probability distributions, it will only be 75% of the data. But as we discussed on the previous slide, our example is approximately normally distributed. So actually a lot more than 75% will be in that range. And that's what we'll discuss on the next slide. So this slide talks about the normal rule, which is kind of like Chebyshev's rule, except it only works for normally distributed data. And it just says that about 68% of the data will be within 1 standard deviation of the mean. So if we look at the graph that we were considering 2 slides ago, we have the center reference line, that's where the mean is located, and then the line immediately to the left of that and immediately to the right of that, those lines are 1 standard deviation away from the mean. So this normal rule predicts that about 68% of the data will be between the line located at 65 and the line located at 71. If you actually count it up, about 151 observations are in that range, and there's 200 total observations, so about 76% are in that range. So, we're not getting exactly 68%, and again, that's just because our sample isn't exactly normally distributed, it's only approximately normally distributed, but it is a pretty decent approximation. The normal rule also says that about 95% of the data points will be within 2 standard deviations of the mean. And this is what we saw on the previous slide. If we count up everything that's between the very far left line and the very far right line, we get about 193 out of 200, which is 97% of the observations in that range. So in this case, the percentage is matching up pretty well. There isn't really anything new on this slide. This slide just shows that the population standard deviation is equal to the square root of the population variance. Now let's discuss the coefficient of variation, which is abbreviated CV. The idea of the coefficient of variation is to measure the amount of variation in the sample relative to the mean. In other words, we don't want to just know how much variation is in the sample, which is what the standard deviation tells us, but we want to know how big that variation is compared to the mean. And the best way to do this is to just divide the standard deviation by the mean. And that's what you see in this formula. It says CV is equal to S over X bar. In other words, CV is just equal to the sample standard deviation divided by the sample mean. We have two examples here, two samples. And for the first sample, the mean is equal to 10 and the standard deviation is equal to 3.6. For the second sample, the mean is equal to 6 and the standard deviation is also equal to 3.6. If we want to calculate the coefficient of variation, we just need to take the standard deviation and divide it by the mean, and then convert that into a percentage. So for the first sample, we take 3.6 divided by 10, which is 0.36, and then convert that into a percentage by multiplying by 100%, and you get 36%. For the second sample, we take 3.6 divided by 6, which gives us 0.6, and if we convert 0.6 into a percentage, we get 60%. So even though these two samples have the exact same standard deviation, the numbers in the first sample are a lot bigger. In the first sample, the numbers are equal to 10 on average. And so a standard deviation of 3.6 is only about 36% the size of the mean. In the second sample, the numbers are only equal to 6 on average. So the standard deviation of 3.6 is equal to about 60% of the mean. So the sample 2 actually exhibits a lot more variation relative to the mean than the first sample does. We've already talked about quartiles. Q0 is the minimum of the data set. Q1 divides the bottom quarter from the top 3 quarters. Q2 divides the bottom half from the top half. Q3 divides the bottom 3 quarters from the top quarter. And Q4 is the maximum. These 5 numbers provide a pretty good summary of what a data set looks like, and for that reason, these 5 numbers are referred to as a 5-point summary. The 5-point summary can be used to construct something called a box and whiskers plot, and that's really what it sounds like. It's a box with whiskers. You can see in the diagram that's what we're dealing with. We have a big rectangle, and the rectangle has a horizontal line in the middle. And then there's a line extending from the top of the rectangle and a line extending from the bottom of the rectangle. And those are referred to as whiskers. Now, you can see in the diagram where everything is located. The bottom of the rectangle is located at the 25th percentile, and it's also called the lower hinge. The top of the rectangle is located at the 75th percentile, which is called the upper hinge. And then we draw a line inside of the rectangle, which is located where the median is. Alright, well, once we've set up our box, we need to figure out how to draw our whiskers. Now, you'll notice that the whiskers extend to a point called the upper fence. The upper whisker extends to a point called the upper fence, and the lower whisker extends to a point called the lower fence. So we would like to be able to figure out where those are located. Here's how we do it. We take our interquartile range, which you'll recall is the third quartile minus the first quartile, and we multiply that by 1.5. And that's actually how long the whiskers are. So the whiskers have a length which is equal to 1.5 times the interquartile range. So if we just take 1.5 times the interquartile range and we add it to the third quartile, that's going to tell us where the upper fence is located. Similarly, if we take 1.5 times the interquartile range and subtract it from the 25th percentile, that's going to tell us where the lower fence is located. Usually most of your data will be located between the lower fence and the upper fence, but sometimes you have some values that are located outside of these fences, and those are referred to as outliers or outside values. These are values that are much larger than the rest of the data set or much smaller than the rest of the data set. And when in a box and whiskers plot, we just plot these outside values individually. So in the diagram here, each of those circles represents an individual value that is outside of the fences. Now we're going to do an example of finding a box and whiskers plot using the data from our histogram of 200 adults' heights. You might want to take a minute to write down the numbers on this slide because these are the numbers we're going to be using to construct the box and whiskers plot on the following slide. Alright, the first thing we want to do is construct our box. So the lower hinge of the box is located at the first quartile, which was 66. the upper hinge of the box is located at the third quartile, which is 70. And so we just draw a box that has a lower hinge of 66 and an upper hinge of 70. Then we want to draw that middle line in the box, and that's located at the median, which is 68. So now we have our box set up. The next step is to figure out where our upper fence is going to be and where our lower fence is going to be. In order to do that, let's find the interquartile range. Well, the interquartile range is equal to Q3 minus Q1. So it's 70 minus 66, which is 4. Then we multiply that interquartile range by 1.5 and we get 6. That means that the upper fence is 6 units above the upper hinge. But the upper hinge was 70, and so 70 plus 6 is 76. And so the upper fence is located at 76. Okay, let's find the lower fence. Well, again, we're going to just take the lower hinge and subtract 6 from that. The lower hinge is located at 66, and 66 minus 6 is equal to 60, and so the lower fence is located at 60. The only thing left to do is construct our whiskers. Now, Dr. Shi constructed the box and whiskers plot a little bit differently in this slide than in the other slide. In the other slide, the whiskers extended from the hinges to the fences. But in this slide, they extend from the hinges all the way to the maximum point and all the way to the minimum point. And that's fine. There are multiple ways of drawing these box and whiskers plots, and different people have different ways of doing it. Different books do it differently, so this is fine. The other way to do it would be to just draw the whiskers from the hinges to the fences, and then we would have some outside values that we would denote by little circles outside of the fences. But in this problem, the whiskers have been drawn all the way to the maximum and the minimum, so we're not going to have any points outside of the whiskers because there are no points above the maximum, there are no points below the minimum. Now we want to talk about some of the different properties that probability distributions can have. This graph illustrates a bimodal distribution. It's a bimodal distribution because it has 2 high points, it has 2 peaks. This is also a bimodal distribution because it has 2 peaks. The peaks don't have to be the same height for it to be a bimodal distribution. As we saw before, in practice, when you're dealing with a sample, it doesn't have as smooth of a distribution as the 2 diagrams on the previous slides. But you can still see that in this example, the histogram exhibits 2 peaks, and so we would refer to this as a bimodal distribution. Of course, it makes sense that if we only have 1 peak, we should refer to that as a unimodal distribution. So the probability distribution given in this example is a unimodal distribution. Again, we're looking at the distribution of an actual sample of data, and of course it's not very smooth, but you can still see that it basically has 1 peak, and so this would be considered a unimodal distribution. When we were talking about bimodal and unimodal distributions, you may have been wondering, what does mode mean? Well, the mode of a data set is just the most frequently occurring value in that data set. So if we look at this first example of the ages of 8 children ranging between 4 and 9, the mode of that data set is 6, because the number 6 occurs more frequently than any other number. This is technically a bimodal distribution because if you looked at a graph of this distribution, there would be a peak at 6, and then it would go back down, and then there would be another peak at 8. But only the number 6 is considered to be a mode because it occurs more frequently than any other number. In the second example, where we're looking at numbers between 3 and 9, there is no mode. No number occurs more frequently than any other number. So this data set does not have a mode. In the third example, the data set also does not have a mode because there is not a single number that occurs more frequently than any other number. The number 4 and the number 7 are in a tie for first place, and in this situation, we just say that there is no mode. Again, this is a bimodal distribution because if you graph this distribution, there would be a peak at 4 and there would be a peak at 7. This slide illustrates a concept called kurtosis. The kurtosis of a distribution is higher if it's steep and it's lower if it's not steep. In this example, the highest kurtosis curve is the blue curve that has a kurtosis of 3. You may be wondering, where does that number 3 come from? There's a pretty complicated mathematical formula that allows you to calculate it, and we're not going to go over that, so you don't have to worry about that. The second steepest curve in this example is the black curve, and it has a kurtosis of 0. And then the red curve is the one that is least steep, and it has a kurtosis of negative 1.2. This slide introduces a new concept called skewness, and it talks about modality in the mean, median, and mode also. But let's start off with skewness, which is really best illustrated in diagram C and diagram D. So you'll notice that in diagram C, we have a distribution that is kind of bunched up, or in this one area, and then it has this long, thin tail that extends to the right. And when you have a long, thin tail extending to the right, that's referred to as positive skewness. Sometimes books refer to this as it being right skewed, but basically the right direction is the positive direction, and the left direction is the negative direction. So similarly, the diagram D, that illustrates negative skewness or left skewness. And you can see that both of these diagrams show the relationship between the mean, median, and mode in each of these situations. So when you have the example part C, the mean is bigger than the median because it's right skewed, and in diagram D, the mean is less than the median because it's left skewed. The other topics that are covered in this slide are modality, as we described before. You see in part A, we have a unimodal distribution, and it's symmetrical. Symmetrical just means that if you look at the left side of the graph, it's a mirror image of the right side of the graph. And in this situation, the mean, median, and mode are all going to be at the same point. Part B is also symmetrical, and so the mean is equal to the median, but it's bimodal. We have two peaks here. Now you'll see that the diagram labels both of those points as modes, and this contradicts what the previous slide said. But this is again a situation that occurs in statistics. You have different people defining things slightly differently, and this is an example of that. So I wouldn't worry about this too much. To be clear, in this course, if we have two numbers that are in a tie for first place like this in diagram B, we're not going to consider either one of those to be a mode, and that's basically what we were saying 2 slides ago. If you have a tie for first place, the distribution does not have a mode. Now we're going to compare some of the properties of the mean and the median. The first thing to notice is that the mean is sensitive to outliers, but the median is not. What that means is that if you have an outlier in a data set, it's going to heavily influence the value of the mean, but it actually won't influence the median at all. To illustrate this, let's take a look at this first sample of numbers that are between 5 and 11. The mean of this data set is 8, and the median of this data set is 8. But let's just say that some kind of error occurred, and the number 26 was accidentally recorded instead of the number 11, and that would result in sample 2. Well, this is actually going to affect the mean quite a bit. The mean is going to change to 11, but the median is still 8 because the middle number in that sample is still 8. And so the mean can be very sensitive to outliers, and sometimes outliers are the result of recording errors or other types of errors. And so that just shows that you've got to be really careful about inspecting your data, making sure that all the numbers make sense, making sure that your data is free of error. That might suggest that we would want to use the median to do all of our statistical analyses, but we actually don't. We use the mean because the mean has a more elegant algebraic form that allows us to build statistical theory around it that works a lot better than the median. And that's what this second bullet is referring to. It says the mean has favorable statistical properties, but the median does not. So all of our formulas later on in the course are going to be based on the mean, not the median. It's important to keep in mind that the mean and the median are not the same thing. So it can be easy to get confused about that. So the median is the middle number in a data set. It always has the same number of observations or below it that are above it. For example, if we look at sample 2 above, the median is equal to 8, and the number of observations below 8 is 2, and the number of observations above 8 is 2. But this property does not hold for the mean. It's not necessarily the case that half of the data is below the mean and half of the data is above the mean, and that's actually shown in sample 2 also. The mean is equal to 11, and so 4 of the observations are below the mean, and only 1 observation is above the mean. Okay, let's just kind of look at a summary of all the topics that were covered in this presentation. Roughly speaking, there were 3 different topics, and the first one was measures of location. We have the mean, which is the average of all the numbers in the data set. You just have to add up all the numbers and then divide by how many numbers are in your data set. You've got the median, which is the middle number in a data set, and then you have the mode, which is the most frequently occurring number in the data set. Percentiles are the points in a data set that divide it based on certain percentages. For example, we talked about how the 90th percentile would divide the lower 90% from the top 10%. And this leads to the concept of quartiles, which are just the points in the data set that divide it into quarters. So those are all measures of location. They kind of tell you where the important features of the data set are located. In particular, the mean and the median kind of describe where the center of the data set is in their own way, although as we described before, they're not the same thing. They're a little bit different. So the median is literally the center of the data, whereas the mean is measuring kind of on average how big the numbers are. Then we turn to measures of variability. These are all attempts to measure how much spread is inherent in the data. The most naive way to approach this is with the range, which is just the biggest number in the data set minus the smallest number in the data set. It's just measuring how far out the data extends from the smallest to largest value. Then we have the interquartile range, which is the distance between the first quartile and the third quartile. And finally, we have the variance, which is really the most important one of these measures, which is obtained by finding the sum of square deviations. You just take each point in the data set, subtract the mean, square that result, add those all together, and then you divide by the sample size minus 1, and that's how you find the variance of a sample. If you're trying to find the variance of a population, you don't divide by n minus 1, you just divide by n. In either case, once you find the variance, to find the standard deviation, you just need to take the square root of the variance. The standard deviation is what you really use to measure the variation in a data set. The main point of finding the variance is it allows us to find the standard deviation. That's really the point of it. Finally, if we want to compare the variance and the variation in a data set to the actual average value in the data set, we look towards the coefficient of variation, which is just equal to the standard deviation of the data set divided by the mean. The last thing we talked about were various distributional properties that a probability distribution can have. We looked at skewness, and if you have an asymmetrical graph that has a very long, thin tail extending toward the right, that's a positively skewed distribution. If you have the opposite situation, a long skewed tail towards the left, that's a negatively skewed distribution. Kurtosis referred to how steeply pointed a distribution is. So if you have a very steep pointed distribution, that's going to have a positive kurtosis. If you have a very flat distribution, that will have a negative kurtosis. And if you have a distribution that's somewhere in the middle, which is, kind of mound-shaped and not too steep but also not too flat, that will probably have a kurtosis that's near 0. But that basically covers everything that was presented in this slideshow presentation. Let me know what you guys think of this. If there's anything I can do to improve, tell me what you think. And as always, please feel free to ask me questions, either in private message through Moodle Mail or in the forums. But until next time, thanks a lot for watching this. Bye.